Until now, we have been covering single degree of freedom systems in free vibrations. That is, there is no forcing, only there is the initial conditions on the system. From now on, we will be considering the forced vibrations, in which case there will be a force acting on our system, as you see f of t over here, f of t acting. That will be a forced vibration. And whenever energy, external energy is supplied to the system through an external forcing, we will consider this to be a forced vibration. There might be external energy might be supplied by a force like this, f of t, or there might be a displacement acting on the system as well. That's also a possibility, but most of the time we will consider the forcing. The character of forcing might be different. It might be harmonic, which means sinusoidal basically. It might be periodic, non-periodic, or random. We will be covering harmonic first, which will be, we will spend a few weeks on this. Then periodic vibrations and non-periodic vibrations. Okay, now the most important part of this forcing, as we said, is the harmonic forcing, in which case the forcing is of the kind, as we said, f of t equals f0 cosine omega t, as you see over here, here, or f0 sine omega t, and there might be a phase angle, but usually we take this phase angle to be 0. But therefore, the forcing is some amplitude times a sinusoidal or a cosinusoidal, which means that you have a forcing function that changes over the time like this with a single frequency. F0 is the amplitude, omega is the frequency, and the phi is the phase angle of the harmonic excitation. We will see that this kind of excitation is very important in the analysis of vibrations. Now we will first consider the undamped system, in which case there is no damping in the system. In this case, we will assume that you have a mass spring system, as we see over here, mass and the spring, and the forcing is a sine or a cosine function. It's here, the cosine function. It can be a sine, it doesn't matter, but important thing is there is no damping in this system. So our equation of motion is mx double dot is equal to k minus kx plus f0 cosine omega t. We can divide everything by m and get x double dot plus omega n squared x is equal to small case f0 cosine omega t, where the small case f0 is force per unit mass, and omega n is the natural frequency of our system. Now we want the general solution, but let's start from the particular solution, that is the solution of the this differential equation. As we know, the differential equations, in differential equations, the solution is the sum of the homogeneous and particular solutions. And we will assume a solution of this kind. The solution of particular solution will have an amplitude of capital X times the cosine omega t, omega being the frequency of forcing, not the natural frequency of our system. We take the derivative of this assumed solution and substitute it back to our differential equation. And what we get will be, for the amplitude, we will get the following term. if you substitute it into your differential equation. Therefore, the particular solution for our system is F0 divided by omega n squared minus omega squared cosine omega t. And note that there is a term omega n squared minus omega squared. If omega is equal to omega n, well, this term becomes infinite, as you can guess. And that means something, as we will see soon. So the total solution for the system is the particular solution. We put it here, as you see. This is the particular solution. But as we know, the homogeneous solution is the response to initial conditions. We still keep it in the solution with unknown coefficients. And those coefficients are to be determined from initial conditions. So we substitute the total solution and enter our initial conditions there so that we can find the most general solution. If x of 0 is equal to x0 and if x dot of 0 equals b0, we can find the most general solution for our system in the following equation, if there are initial conditions also. Okay. Now, as we have said before, the solution is not defined defined for the case where the natural frequency is equal to the forcing frequency, because it produces, as we see over here, a division by 0. Okay, this is something you should be noting. And if the forcing frequency omega is not exactly equal, but close to omega n, then the particular solution, this term becomes close to 0, so the amplitude of the response would be very large, especially in the particular solution. Okay. Now, let's apply our initial conditions and let's take the simplest possible initial conditions. Let's say that in our system, like this mass spring system, K, we apply a force of f of t equals f0 cosine omega t, okay? And then the initial conditions are 0. We suddenly start applying forces. So x of 0 is 0, x dot of 0 is 0. From the previous page, what we are left with is this term, f0 omega n squared minus omega squared cosine omega t. Well, there should be a closing of the parentheses here, minus cosine omega nt. Okay, in which case we can define a called delta static, which is f0 over k. And when you can write our x of t in the following form. Now, this is a function which is, which is a sum of two cosines, cosine omega t, forcing frequency, and cosine omega nt, natural frequency. The problem is when omega equals omega n. When omega equals omega n, as we see over here, 1 minus omega over omega n is 1, 1 minus 1 squared is 0. And then on the top you have omega equals omega n, again gives you a 0. So we have a 0 over 0, which is indeterminate. So in this case, in order to obtain a real solution, we want to use the L'Hopital's rule. When you have 0 over 0 in a limit, you have to take the derivative of the numerator and the denominator, as you should remember from calculus. So when you take the derivative of the numerator and the denominator, our solution becomes, derivative of the cosine. By the way, we are taking derivative with respect to omega, not with respect to t. That's very important because omega is approaching omega. So what we get will be, as you take the limit, eventually the following expression: omega nt over 2 sine omega nt. And beware of this term, omega nt over 2. If you plot it over the time, it is basically a growing function like this. This is t versus, let's say, omega nt over 2. So, and you have a sine function that oscillates around it. But as you see, the amplitude of the sine function keeps on growing. So, when our driving frequency is equal to the natural frequency, that is the frequency of forcing, is equal to the natural frequency of the system, the amplitude of vibration, as you see in this picture, but at the bottom, okay, here, it just grows and grows and grows and grows until the physical system breaks down, okay? This is the phenomenon called the resonance, actually, because in this case, when the natural frequency is equal to the forcing frequency, when they are exactly the same, the external forcing f of t keeps on adding energy to the system, and the energy of the system increases all the time, which means that the amplitude of oscillations is going to grow and grow and grow. And at some point, the system is going to break down if it's a physical system. So the resonance for an undamped system, by the way, remember that this is the undamped solution. If there is damping, this doesn't happen, but the amplitude can grow to a very large value. But if for an undamped system, it just grows to infinity. So x of t goes to infinity as t goes to infinity, let's say. This is called resonance, and the resonance is a very detrimental effect on physical systems. For example, the Tacoma Narrows Bridge was destroyed because of the resonance in 1940, because the frequency of the wind vortices was equal to the natural frequency of the bridge, which caused very large amplitude vibrations and destruction of the bridge. And there are many other examples of resonance. So in general, the resonance is something to be avoided in vibrating systems.